All right. So derivatives in the shape of curves or the shape of graphs. So just some good stuff about what a derivative and a second derivative will tell us about a graph. All right, the mean value theorem. This is a big thing. Often a justification or a reasoning on the free response section of the AP exam. If f is a differentiable function, in other words, you can take the derivative on the interval from a to b, then there exists a number c between a and b, such that the derivative at c is equal to the slope of the secant line joining the two endpoints. F of b would be the y value at one end minus f of a, y value at the other end, divided by b minus a. Sometimes it's written, multiplying both sides by, by b minus a. So you get f of b minus f of a equals f prime of c times b minus a. A couple of things about this function being differentiable. So that means that the function on that interval has to be continuous. It can't have any sharp points. Sometimes they're called cusps, like an absolute value where the vertex is. That would be a cusp or a sharp point. And it can't have an undefined tangent line, undefined slope for a tangent line. So some important pieces. I've seen problems on the AP exam that will ask, does the mean value theorem guarantee that? And then they'll make a statement. But they'll have a function that's not differentiable or it's not continuous. Something happens that there's a point where the derivative does not exist. And so you would say no, because at this point, the derivative does not exist. Yeah. All right. So a test to tell whether a function is increasing or decreasing. Are you Googling to make sure that I'm right? Or? All right. So if the derivative at some point c is greater than 0, then the function is increasing. Positive slope for our tangent line, function is increasing. That should kind of make sense, I hope. Negative slope of our tangent line, so the derivative is negative, then the function is decreasing. All right, here we go. Where is the function 3x to the 4th minus 4x to the 3rd minus 12x squared plus 5 increasing, and where is it decreasing?
first? Or
What's that?
the first thing to just find the derivative?
Yep. Yep, so the first step, find the derivative. Three x to the fourth, its derivative would be minus 4x cubed. Yep. Minus 12x squared. There we go. Plus 5, 0. Okay. So that's great. And now we want to find where this function is positive and negative. But the easier thing to do is to figure out where is it 0, and then use where it's 0 to tell what's happening on either side of that 0, rather than just try and pick a point and see if the derivative is positive or negative. So I would set the derivative equal to 0. And do that fun thing that we like to call factoring. X squared minus x minus 2 is that factor.
X minus 2, x plus 1.
There you go. Yeah. So that would mean each factor set equal to 0. And we have 3 places where our derivative is 0. So, and remember, where the derivative is 0, we refer to that, easy for me to say, we refer to that as a critical value or a critical number. So here's the way I would approach this. So I know this is my derivative. And I've got -1, I've got 0, I've got 2. And I would just take a value on each interval. So take a value that's less than -1, like maybe -2. Plug it into our derivative, and I would plug it in to the factored form of the derivative. I don't care what the exact value is. All I want to find out is what sign does the value have? Is it positive or is it negative? So if I chose -2 and I plugged it in, 12 times -2 gives me an answer that is negative. -2 minus 2 gives me an answer that is negative. -2 plus 1 gives me an answer that is negative. So I have a negative times a negative times a negative. If I'm multiplying 3 negatives, my product is negative. And I would just mark it. Pick a value between -1 and 0. Maybe -1/2. 12 times -1/2. Negative. -1/2 minus 2. Negative. -1/2 plus 1. Positive. So I multiply a negative, negative, and a positive. My result is positive. Pick a number between 0 and 2, maybe 1. And if I plug it in, I get positive, negative, positive. And when I multiply two positives and a negative, my result is negative. And pick a number greater than 2, like pi. We have a positive, and a positive. So for our original function, it is increasing from -1 to 0. It's also increasing from 2 to infinity. We use the parentheses here because technically at -1 and at 0 and at 2, it's not increasing or decreasing at that point. And then decreasing negative infinity to -1, and from 0 to +2. Oh, Mr. Gingrich, that's easy. Good. Wait until we throw some different functions at you, then you can complain. A couple of things that you want to be aware of. Make sure you know the domain of the function, the values for x that work. For instance, if it's a rational function, or if it's a logarithmic function or an even root function, it's going to limit your domain. And so just make sure that you're aware of that. For instance, square root can't be increasing or decreasing from -infinity to 0 because it's undefined when we have negative values. So again, be aware of that. The first derivative test, you didn't know you were going to have a test today. You're actually going to have 2 of them. Yes. First derivative test. Suppose that c is a critical number of a continuous function f. So what does that mean? That means at c, the derivative is 0. If the derivative changes from positive to negative at c, as we're moving from left to right, then f has a local maximum at c. So what this is saying is if f goes from increasing to decreasing, we have a maximum. If f prime changes from negative to positive at c as we move from left to right, f has a minimum. So we're going from decreasing to increasing, giving us a minimum value. If f prime does not change signs at c, then we don't have a minimum or a maximum. And that can happen. Common example of when that happens is when you have x cubed. its derivative is 3x squared. 3x squared is 0 at 0. The derivative as I approach 0 from the left is positive, and as I go from 0 to the right, it's positive. So I don't have a change in sign. I don't have a minimum or a maximum. All right, concavity test. This is not what you go into the dentist for, and they poke you with that sharp, pointy metal thing. All right, that's not the concavity test. Concavity test deals with the second derivative. If the second derivative is positive for all values of x on an interval called I, then the graph is concave upward on I. Concave upward is U-shaped. It's like a parabola. A parabola is always concave up. If the second derivative is less than 0, if it's negative for all values of x on some interval, then the graph is concave down on that interval. And concave down would be kind of like N-shaped, or the opposite of a parabola, negative x squared. Yeah,
Wait, what does the I mean?
that's just an interval, okay? On all x in some interval I. All right, here's your second test for the day. The second derivative test. So we went kind of through the first derivative test, and that was, and basically that little number line thing we did to tell where it was increasing or decreasing would be great to use with the first derivative test. If you don't like that idea, there's the second derivative test. Suppose our second derivative is continuous near some value c. If f prime of c is 0, so if c is a critical value, and the second derivative is positive, so it's concave up, we have a minimum value at c. And so if you think about that concave up, it's like a parabola, and that vertex would be a minimum. I always mess this one up because I always think if it's positive, it should be a maximum, but because it's talking about concavity, it's a minimum. Probably shouldn't have said that. Now I'll probably mess you guys up. If c is a critical value, the first derivative is 0, and the second derivative is negative, we have a maximum, a local maximum. So think about that. It's an upside down parabola. That vertex is a maximum value. Again, if the first derivative is 0 and the second derivative is 0, we don't have anything. It's not a minimum or a maximum. The point where the curve changes its direction of concavity. So where the second derivative changes from positive to negative or from negative to positive is called a point of inflection. All right, so here's a nice little video about the mean value theorem. And in order for you to hear it, I'm going to need to hook up some speakers. This is quite possibly the most exciting math video that I've ever seen. Sense a little bit of sarcasm there. Yeah.
Last year, while I was traveling to join our bunch, the Blue Ridge Singers on tour, this year college boy asked me if I want to ride. I allowed as how I did, and I got in. Pretty soon we come to what they call a throughway, which is a road you got to pay to ride on. They gave us a ticket when we got on, which read on the front, Syracuse 9 a.m. And then we really took off down that throughway like a pair of scared rabbits. That speedometer went up and up, and I saw them mile markers keep a-passing. Well, friends, I see a sign saying it's a Buffalo exit, and off we go. But before the college boy could even pay, the ticket taker, he hands his ticket to the police, and the police ups and says, "You've been a-speeding. You've been 150 miles in 2 hours. So someplace you've been going 75 miles an hour." Well, the college boy, he tries to lie out of it. But the police, he says, "Don't they teach you calculus at that college you go to?" The boy, he says, he flunked it last year and is taking it again, but he don't like it a bit. Well, the police says, "You better learn some." We'll just draw a graph of this here problem we got here. We draw vertical and horizontal lines. We measure time horizontal and distance from New York vertical. Time he calls T.
That's what you get, Nate.
Then he ups and puts numbers on these lines. He calls them axes. And he marks up 2 numbers real plain on what he calls the T-axis. Now, the police says, at 9 o'clock, we were 280 miles from New York. So we'll just plot a point here and call it 9280. And he ups and says at 11 o'clock, you come here to Buffalo, which is 430 miles from New York. So he puts this other point down and calls it 11430. Well, you know, he draws a little curved line between these points and says this is pretty close to the graph of that function f. He says this curve has a height that's how far from New York you are at any time t. Then he draws these two lines and says one is how long it took, 11 minus 9, and the other is how far you come, which is 430 minus 280. And so somewhere we had a speed of 430 minus 280 over 11 minus 9, which is 75 miles an hour. He calls this F prime of C. Well, friends, his college boy tried to agree with him, thinking he might get out of a fine that way. But the police, he says, if the college boy had been driving correct, he wouldn't be here till noon, no way. So he says, we'll just learn you some calculus now. So the police, he says, if A and B any times on your trip, F of A will be how far from New York you are at time A, and F of B will be how far from New York you are at time B. Now, says he, I claim the quotient F of B minus F of A divided by B minus A is your actual speed at least once from time t equals A to time t equals B. We already know speed is the derivative of the distance function. Well, friends, it seems to me as how the college kid has had enough, but the police, he don't quit. He says, more generally, you ought to know for what kind of functions this is okay. Let's look at the graph of a function again. We'll take a look at 2 points on it, A, F of A, and B, F of B. We can draw a line through these points, and this line is the graph of some linear function. Now, he claims, this here line has a constant slope, and he even writes a formula for it. But, he says, he just don't know for sure about the slope of this here curve. But maybe somewhere between A and B, the slope of the curve is the same as the slope of the straight line. Then he writes what maybe is the slope of this curve for this point. Now, the police, he don't let up. He asks the kid if he knows the mean value theorem. The kid, he says you got to learn it by Monday. Well, says the police, we'll just write it down right here and prove it. If F prime exists on open AB, and if F is continuous on closed AB, then for some C on open AB, F prime of C is F of B minus F of A over B minus A.
All right, I think we'll stop there. If you want to, you can Google, I think it's on YouTube, the theorem of the mean policeman in calculus, and it's there's more, but it's a good possible application of the mean value theorem. Plus, I like to hear that southern drawl that the narrator has. am also going to hand you a nice little review. Some might say a practice quiz for you to practice for section, yeah, for next week. For sections 1, 2, and 3.
We didn't even do section 2. I'm just saying, I don't even remember that one.
Yeah. Well, the good news is you have a week.
Oh, Mr. Beaver, it's all right.
All right.